is there intelligent life out somewhere in the universe? Could humanity contact it, talk to it? Could we get destroyed by it? What wonderful and interesting questions. So, how might we actually detect an alien species? An interesting method would be to search for communications, send signals throughout space, and somebody might pick them up. A bit like how we send broadcasts and other signals to other human beings. Maybe there is some alien species sending signals across the galaxy that we might be able to intercept. If any alien species worked out how to broadcast in a frequency range that we can detect, we should be able to pick it up. So, if we cast our minds back to the year 1959, scientists were starting to argue that radio telescopes had become good enough and sensitive enough to perhaps do this, perhaps intercept the transmissions of broadcasting alien species. So now another interesting question comes up then. How many possible alien species could we find? How do we estimate the number of alien species that could potentially be communicating with us? And this puts us into the position of a man called Frank Drake. He's hosting a meeting on a search for extraterrestrial intelligence, and in preparation for this, he writes down the things you need to know if you want to predict how difficult it is to detect extraterrestrial life, or more aptly, how many aliens are going to try to be communicating with us, and therefore what are your chances of success. What he realises is that he can use this to get a number of detectable civilizations in our galaxy from these things that you need to know. So what I'm going to do now then is try and roughly rederive something similar to what he would have done and work out how we can estimate the number of potentially communicating alien species. First of all, let's talk dice, because if we're going to do this, we're going to want a way that uses probability, and dice are a wonderful way to talk about it. There's not much to go on in estimating the number of possibly communicating alien species, but perhaps we can split this up by asking, if I roll many dice, say I roll 600 dice, how many sixes do I expect to get? A lot of you, certainly anyone who knows a bit of basic statistics, will say, well, we can't know for sure, but we predict around 100, because in terms of probability, the expected number of outcomes you get is equal to the number of possible chances, if you like, the number of possible rolls, multiplied by the probability of getting that answer. So in this case, your expected number of sixes is the number of rolls of the dice multiplied by the probability of getting a 6. So how does this relate back to aliens? If we want to think cleverly, if we want to reduce this problem to something that we can actually put some scientific graft into, we'll say that the number of alien species which could communicate with us is equal to the number of possible habitations for these alien species multiplied by the probability that they get to the stage where they can communicate with us. The next step before we get into anything clever is to sort out time. You see, the probability that we want is going to be a fairly rough estimation. We don't want it depending on time, because that's going to throw in an enormous amount of galactic evolution, stellar evolution, lots of horrible things. We don't want that. What we're going to do is deal with an estimate where any terms involving time cancel out to give us a fixed probability, which we'll then use to get a fixed rough number of alien civilizations at any time. Why is this important? Well, because time is definitely going to get involved. Let's say an alien species develops, there's going to be a certain length of time which they send these signals out for. There's certainly going to be an average length of time, because some of them are going to likely send signals and then stop sending signals, possibly because they die out, they get hit with some tremendously bad luck, or they just crank up and decide, no, we're not doing this anymore, this is dangerous, or they develop something better that we can't detect. So there's going to be a lifetime of aliens sending signals. And we need to make sure that this fits in our formula without messing anything up. The way we're going to do this is we'll replace the number of possible rolls of the dice with, if you like, the rolls of the dice per unit time. If you think back, instead of saying we roll 600 dice, you could say we roll 6 dice every second and pick up the results. And as long as we specify how many sixes to expect in a time frame of so many seconds, we should come to the same sort of answer. We can deal with time in this way. This gives us a start of the formula for estimating the number of possible alien civilizations we can communicate to. That n is equal to the rate at which habitable planets for alien civilizations come into being, which is in effect what we did to cancel out the time problem, multiplied by the fraction of those planets that actually develop life which can communicate with us. That's the probability of rolling a 6 part of this, multiplied by the length of time that those communications last for. So what we're going to do now is a bit more like what Frank Drake did. You see, he worked through this the other way around. He worked out what you need to know to predict how hard it's going to be to detect extraterrestrial life, and worked from that to a formula for this number. So what we're going to do is we're going to start splitting this into something sensible related to how hard it will be to predict extraterrestrial life. We'll start with the planet formation bit, because that is far simpler and we can work this out using our knowledge of astronomy. How are we going to estimate the rate at which habitable planets form? Let's split it into the parts. We're going to say planets form around stars because we're being simple, and astronomers know how to estimate the rate of star formation in a region. We then multiply that by the fraction of stars which have planets, and multiply that by the average number of planets that could develop life per star. This is starting to look a lot more like the Drake equation. We'll call the rate of star formation R star, the fraction of stars that have planets F sub P, and we'll call the number of habitable planets N sub E for number of Earth-ish planets or something similar. The interesting thing is, you see what we did here. We started off with a number that we had no idea really how to estimate, and split it into feasible steps with things that we might be able to start putting numbers on. However, now for the more difficult part, how do we split the probability that life that can communicate with us occurs into a reasonably sensible set? Let's think of what it means for a civilization to be sending communications out towards us. We need to find the probability that they exist, and how about we assume that sending communications requires being some way up the alien life tech tree. So what we need to do is to work out the probability that this alien life gets up that tech tree without dying out. We start off with a planet which is potentially habitable for life. That's what we ended up with in the first part of this formula. So how do we get from there to aliens communicating with us in a well broken down series of probabilities? We multiply each of those probabilities together, we end up with the fraction of those planets which have alien life which passes each threshold. So first step is fairly obvious. What fraction of the planets that could develop life actually do develop life? Let's call that FL, and we'll put it into our formula. However, thinking about life, some of it's not very intelligent. So I think most of us would say it's reasonable that sending out communication through space is only something that life can do if it's past a reasonable stage of intelligence. We're not going to really delve into much detail on that, but we'll say that the next step in our term should be the fraction of alien species which has developed intelligent life. So we start with the fraction of habitable planets that develop life, and the fraction of that life that is then intelligent. Call it Fi. put it in the formula. However, intelligences are not enough. There was a time when humans were still the same humans as us, but of course they hadn't developed technology to send signals into space, and given how long humanoid species have been around on Earth, there's a possibility that a planet could develop intelligent life but not have it ever communicate. So we'll call a fraction of these civilizations which could develop the technology to communicate signals F sub c, for the fraction of communicating life. We've now got from the start goal to the end goal we wanted, splitting it up into more sensible steps. Putting these together, we give a formula to estimate the number of alien species in our galaxy. What we do, we take the rate of star formation and multiply it by the fraction of stars which form planets, and then by the average number of habitable planets which form around these stars. This gives us the rate at which habitable planets form. We then multiply this by a series of stepping stones which an alien species must overcome to send out communications into space. Multiply this by the length of time these signals last to obtain a static estimate for the number of alien civilizations in our galaxy that we can communicate with. That equation that I've just ran through is called the Drake equation. That's what Frank Drake ended up with back in the 1960s. It doesn't actually constrain how many civilizations we can communicate with, unfortunately, but we can estimate star formation rates, and our advances in searching for extrasolar planets could help with the start of that equation, finding, say, the number of habitable planets or the fraction of stars which have planets around them. The last few terms of the equation are very much guesswork. We have very little ability to estimate the fraction of planets containing life that then go on to develop intelligent life. We only have one planet that we know of at the moment with life on. We certainly only have one planet with intelligent life on. We have a hard time also working out the fraction of intelligent life forms which could send out communicating signals. Again, we've just got ourselves, and this is largely guesswork. This means that actually the Drake equation doesn't really produce useful estimates. Depending on your assumptions and how you put values into these terms, you can get estimates for the number of communicating life forms in the thousands, meaning we're likely to find nearby civilizations, or far less than one, and we could be the only civilization in our galaxy. But here's what we can do. We can look at this the other way round. Say we don't find aliens nearby. Despite our best efforts, we conclude that it's highly unlikely there are aliens near us, and the number of communicable civilizations in our galaxy is a handful at most. Now we have to ask ourselves why. And while at first this seems like an incredibly difficult problem, we can then use the parameters that we've put in the Drake equation to give us a scientific path to follow. We can work out which parameter is the thing that's preventing this. Could of course be something else, that there are large amounts of communicating civilizations that just don't communicate. However, there's a good likelihood that we can find some insight into this from looking at the terms in the Drake equation. Perhaps habitable planets rarely actually develop life, that the development of life from the non-living matter on the planets is an incredibly unlikely event. Or of course it could be that intelligence is the block. Perhaps life grows in an enormous amount of places, but only the fraction developing intelligence of the level required to send these signals is very low. A good point made on this is often that of the enormous variety of life on Earth, there's only one species that's sending out these signals. You can now see one of the uses of the Drake equation. It's a thinking mechanism. It might not be giving us a clear numerical answer to how many alien species there are, but we've turned a question that at the start was basically impossible to do much with into something where we can get into a lot of interesting and useful discussion. The other thing is, because we worked through this in a logical manner, you can now see how to modify it to take into account other factors Drake didn't consider. Let's say you wish to add a fraction to represent the fact that sending some random radio signal is not the same as sending a dedicated message into space. You think that perhaps there are a lot of civilizations that could, but definitively trying to find other species may be a roadblock. you know exactly where you would add that, you know how to put that fraction into the equation. Or you could consider that maybe intelligent life could rise multiple times on the planet. You can think of a few ways to put that number into the equation. Alien life being found on moons maybe, as well as other planets. Again, you can adjust things to fit that in. And that, I think, is the real brilliance of the Drake equation. It's a great tool for learning, in a way, how to pick a problem and separate it down into parts in a way that gives you far more use than you may have considered if you just looked at the problem flat on. Next time, what I'm going to do is delve far deeper into what made up some of the last part of this talk. So far, we haven't found any alien communications, and I mentioned probing the Drake equation as a way to work out why. So next time I'm going to go through that in more detail. There's a very specific idea of asking the question, why are there no alien species? Why haven't we bumped into any alien species? Referred to as the Fermi paradox, and I'm going to take a longer look at that.